You'll often see me use sort of a script K, and it's equal to 1/2 the mass times the velocity squared. The units are going to be in joules. Okay, so it's a contrived formula like Newton's. It's essentially equal to a kilogram meter squared second squared, and this represents meter, and this represents mass. So I have to be careful about my units here. So just be mindful that all this stuff comprised are in units. And this piece right here, this is our velocity. So kinetic energy is basically a moving energy. So we're going to need to be moving in order to see this type of energy formulate. The other type of energy that we're going to look at is that of potential energy. And we're going to look at potential energy in a couple different ways. We're going to look at gravitational potential energy. That comes by way of moving an object, typically in an upward position, to kind of foster and gain energy, if you will. So in a system, in our systems, we'll see that we can't create nor destroy energy. So what we're going to be doing is we're going to basically keep our system closed or conserved. That means that the energy that we have before is going to equal to the energy that we have after. So for gravitational potential energy, you'll often see me write a script U, and then maybe we'll have something that looks like this, and it's equal to some mass times gravity, the acceleration due to gravity, at 9.8 meters per second squared, times some height. Or you may see me write mgy. And so how this is going to look, let's just say that we have some building here, and we take an object and we drop it from this building. But right before we drop it, we notice that it has some height. So let's just say it's at 5 meters above the ground. And so the potential energy at this point is equal to whatever the mass is. And let's just say the mass is 10 kilograms. So it's going to be the 10 kilograms times the acceleration due to gravity times the height. Again, we need to be in SI units here. So if you were to multiply all that, you should get 490. And the units, again, are in joules. Okay. And so the other type of potential energy that we're going to have the potential energy of a spring. So this is called elastic potential energy. And this is going to come by way of compressing a spring, and it's going to equal to 1/2 the K value. We looked at that when we talked about Hooke's law. The units are going to be in, again, in joules. K is our spring constant. And we'll see that that unit is going to be in newtons per meters. Okay. And so, again, we're going to look at several types of potential energies. Oh, and for this one, X is just the displacement. From equilibrium. So let's talk about that. Let me add a page here before we get into one of these problems. And so if we're looking at a spring, so let's just say that this is the floor, and I put a spring in here, and I attach it to the floor, and maybe I have, in some cases, we'll have an object there. In some cases, we won't. So let's just not distract ourselves with that object. So we have a spring, and this is just, let me point to it here with my highlighter. And so this right here is just some wall or something to push on to give us some leverage. And what we're going to do is we're going to compress the spring. So let me just duplicate that over again, except this time I'm just going to move the spring outward a little bit and give it a little bit more length. Okay. So actually I've pulled the spring, so let's do as I said I was going to do. So let's flip-flop these positions. We're going to compress the spring. We start off with the picture on the top, and we compress the spring on the bottom. And so in the top instance, we'll say that this is uncompressed or in equilibrium. Sometimes you may hear it as unperturbed or non. Okay. And then you apply some force to it to get it to move a certain distance. In this case, now this is compressed. And it's compressed a distance relative to where this thing started when it was at rest. So let's just say that this thing got moved a distance of X. So once we do that, we're storing energy, if you will. We use some work to move that spring, and we're storing energy, and thus we have some potential energy. Okay. All right, so let's look at an example here of gravitational potential energy. And these are some problems from your book. I'm probably not going to be more than an hour for this in case you're trying to kind of time yourself. So we're going to take a ball and we're going to drop it from some height. So we'll have, again, maybe some building, and here's our ball. It's going to start moving at some particular point. So it'll start going down, and then the object is going to bounce, start to go up. And then only go up to a certain distance before it maximizes its height. The ball starts off at a height of 5 meters. And the first bounce is at 3 meters. We want to know how much energy is lost to non-conservative forces. So let's talk about these various forces. Now, the forces come by way of, the forces come by way of things that we already know. So the force of gravity is one of the forces that we're talking about here. It's the only force primarily that's going to be acting on the object. There's no initial thrust of the ball in the downward sense. It was just simply released. So I don't want you to kind of be misled. So this part right here, there is no initial speed, if you will, in that area. It is simply released. Okay. Let me erase that. Okay. So let's talk about a formula as we go through this. So one of our key pieces here is we're going to talk about conservation of energy, as I said before. And we've talked about the two types of energy, but when we combine those energies in our system, it's called mechanical energy. And all mechanical energy is, and we'll typically call it E, all mechanical energy is, it's the sum of kinetic plus potential energy, or energies. Okay, so for us, we're going to have some initial energy of the system right here. We'll call it E naught. And remember, the object, before I release it from my hand, this is my hand, it has no initial velocity. So all I'm doing is I'm just simply releasing it with no initial velocity. That's why I kind of erase those dashes. And then at our second point, we'll call it right here, our E final. It's going to also have some mechanical energy. And so the theory behind this, again, is that E naught is going to equal to E final. I believe in your book, the book uses E1 and E2. E1 being in the initial, E2 being the final. Okay. So let's write down what the energy is at the top position. So E naught, our initial energy, is going to equal to, remember we have gravitational potential energy, and our initial height, we'll call it H naught. And we also, for mechanical energy by definition, we have kinetic energy. So 1/2 m, we'll call it V naught squared. And we'll clean that up in just a second. And then our second piece, which comes by way of the final kinetic energy, the final mechanical energy, again, we'll write down mg H final plus 1/2 mv final squared. Okay. And so this matches up with that, and this matches up with that. Okay, so let's clean this up a little bit, because not all of these values are going to be necessary. Some of them are, some of them aren't. And we also need to know what we're looking for as well. So it says how much energy is lost to non-conservative forces. I didn't define that yet, so let me just work through this part, and then I'll define what non-conservative forces are. It's basically the forces that are going to be, in this case, we're looking at non-conservative forces. So it's going to be those that force that's due to the drag or the air resistance here in this problem. A lot of times it'll be friction. All right, so let's throw away anything that we really don't need in that last line. So we know that all of these values for in the first term are good, so we'll keep all of those. We don't know the mass yet, but we'll be fine with that. And remember, I emphasized the fact that the V naught was 0 because I didn't give it any initial thrust, so that's going to go to 0. And let's go to our third term here after the equal sign. In our third term, our H final, well, that's probably going to be necessary to use and utilize. So we'll keep that. But when this ball comes to a high point right here, when it reaches its max, its velocity or its final velocity is 0. So that part is going to get thrown away. And so we'll send that to 0. And so let's see what we have now. So we'll have mg h naught is equal to mg h final. Okay. And what we're looking at here again are the comparisons of the two different energy states. So E naught and EF are defined. So let's, we're not going to plug in any numbers here per se, because all we're going to do is just basically be able to find, you can cancel out the M's and cancel out the G's, but that's not going to be very helpful to us. We want to figure out the comparisons of the two different energy states. And so how about we write for E naught? So E naught is going to equal to the mass times 9.8 times 5. And for E final, it's the mass times 9.8 times 3. And we want to figure out how much energy was lost. So if you think about well, if you think about discount price, if you will, it's sort of like that, how much money is discounted. So you've probably come across energy or percent differences, if you will. So in this case, our energy lost is going to be sort of a comparison between our initial energy and our final energy compared to our starting point, which is our initial energy. Okay, so we're trying to figure out the percent of energy loss. So let's now do the math. And so in this case, and I put the absolute value here because I just want to make sure that I get a positive value out of this. Okay, if you get a negative value, it doesn't really matter. You'll see, you'll just see that numeric value, but I like to get positive numbers. So let's see what I get. So how about, when I did this, I didn't even multiply and plug in the G. So how about 5 times mg minus 3 times mg, all divided by 5 times mg. And then we can clean this up. So on the top, we get 2 mg. On the bottom, we get 5 mg. The g's cancel out. The masses cancel out. We get 0.4 or 40%. Okay, so there's a 40% energy loss in this scenario. So what you're going to need to just kind of pick off here is you're going to need to pick off and distinguish between conservative and non-conservative forces. So I don't go into a long instruction on that because we're going to see a formula that really is going to make everything kind of tie together. But some of the conservative forces that we're going to be wanting to focus on are going to be gravity, the spring or elastic force. Later on in your next class, you'll see the electrostatic force. And for non-conservative forces, we're going to be talking about a lot of friction, air resistance, tension, and in some cases, engine propulsion. First, propulsion. First being friction is the primary non-conservative force that we're going to be working with for this class. Okay. Next problem. Let's look at problem number 5. So here we get into the spring. And remember what springs do. As I said up above here, we have these springs that when we push them or pull them from equilibrium, we're able to create some potential energy. So let's use this as a picture here. And let's paste this in. Now let's read the problem. It says that it requires 7.5 joules of work to stretch a particular spring 2 centimeters. And from its equilibrium length or position. How much more work will be required to stretch it an additional 4 centimeters? Let's grab the other picture so I don't have to keep redrawing these things. And so we'll use this first picture. Let's see, we're going to go from an uncompressed spring to a compressed, a pulled stretch spring. And so let's again flip-flop these 2 pictures, positions. Let's put that over here on the bottom. Let's put that up top. If I can grab all that. Yep. So we'll grab that. Let's delete some of this. Okay. So the top is the formula or the spring at rest. And bottom is being stretched. All right. And so we're going to pull it some distance. It says that we're going to pull it in this direction, say, and it is 2 centimeters. And let's go ahead, because we don't like non-SI units. Let's put this in SI unit form and change that to 0.02 meters. Okay, so we pull that spring out 0.02 meters in this direction. Now let's write down what it tells us. It said that the work that it's going to take to move the spring is going to be, what was it, 7.5 joules. So again, work is a measure of energy. Now, for this particular problem, remember the work that's being done on this spring is going to be, let's see, we introduced that back here, is going to be equal to the elastic potential energy. So it's going to be equal to the 1/2 kx squared. So this is equal to the 1/2 kx squared. All right. So work is, in this case, equal to the potential energy. Now, let's see what's given here. It gave us that we moved the spring 0.02 meters, and let's plug in and see what we have. We'll leave the units off. So 7.5 is equal to 1/2 K. We don't know K times 0.02 quantity squared. And when we solve this, we should get that K is equal to 37,500 newtons per meter. So in other words, it takes that much force every time you move it a single meter. That's sort of the spring number to let you know how thick or how strong a spring is. So that's a pretty strong spring. Okay, so that's probably a spring that's going to hold back maybe a couple maybe two train cars together or trucks. I'm not sure exactly the value, but it's going to be a pretty big spring. All right, so that's going to be an important number for us because we want to figure out, we want to compare it to the work that it's going to take to move it another, it says another 6 centimeters. Okay, so we're going to move this second spring. Let's move our work down just a little bit. And actually, we're going to put an extra page on here. Okay. So we're going to move this last spring that I have drawn another. Sorry, class. Let's move that down. I want a blank page there. Okay. So we're going to move this last spring another 0.06 centimeters. Let's duplicate that. Start right here. Grab the spring piece, move it out a little bit more. Say about there, and just extend that line a bit. So now we're looking at that. Okay. So now we're going to move it from this point, 0.06 meters from here. Okay. So let's see what it takes here. Let me make sure I read that right. So how much more? I'm sorry. It said to move it an additional 4 centimeters, which would have gotten me, gotten me 0.06 centimeters away from equilibrium. So this distance right in here is the 0.06 meters. Okay. And so let's see what we get from that. Let's move this work piece up here a little bit. Compress that down. Remember that it ties in with that. And let's do this again. So the work on the spring, that's going to take us 0.06 meters from the initial starting point, is equal to, again, 1/2. Now we know the spring constant this time. It was that 37,500 newtons per meter. The displacement from equilibrium is equal to 0.06 meters. And when we do the math on that, we should get 67.5 joules. So what does it take to get us to that spot from the previous spot? So it's going to take an additional 60 joules to move from, we'll just call it B to C. We're always, it asks us to compare it from the previous spot. Okay. All right. That was problem number 5. Next problem I wanted to look at was problem number 12. Problem number 12 involves Tarzan and Jane, and Jane is going to be running at top speed and is going to grab a vine that hangs vertically from a tree, and we're going to try and figure out how high she can swing upwards, and we're going to try and figure out, does the length of the vine affect your answer? All right, so let's draw a picture here first. So here's our picture of Jane. She's going to grab this vine here. Remember, she's running at some initial speed of 5 meters per second. And then she's going to swing up to here, say, holding on to the vine. And she's going to swing up a certain height. So let's draw that a little bit more meaningful to us. So how about we move this person down a little bit. Same person. She's going to swing, and she's going to travel up a certain distance when she swings. And we'll call that h of f. This distance right here is h of f. That's what we're trying to find. So let's go to our theory here that says that E naught is equal to E final. And let's write out our formula. So we'll have that 1/2 mv naught squared, which is our kinetic energy, plus mg h naught is equal to 1/2 mv final squared kinetic energy plus mgh final. Okay. And so what we're going to want to do here, and what we can always do, is we're going to affix a certain spot to be equal to 0. Now you might think that setting the ground at 0 would be the ideal spot, but in this case we're probably going to want to set H naught here equal to 0, or 0 meters. So where Jane starts, which is right at the base of that cliff, she's going to grab that vine, she's going to swing up a distance, is going to be our H naught. All right. So what does that mean for us? Now, potential energy is a relative number, and what it means essentially, so relative to that particular spot, relative to that cliff, our potential energy is 0. And so we kind of, if you will, change the reference point. So this point right here is going to go to 0. The other thing that we probably already know is that when she swings to this upward spot, she's going to max out her height, and she's no longer have any velocity. So in that case, the final velocity is 0. So again, let's rewrite this. So we have 1/2 mv naught squared is equal to mgh final. So let's see if we can solve this for H final, if we have enough information. So we know that the masses can cancel out. And if I look at this, I can see that I have everything except for H final. And so I should be able to solve this relatively easy. So we multiply both sides by 2, and we'll get, how about V naught squared is equal to 2gh final. And then now we'll divide both sides by 2g squared. And so H final, when we plug in, I won't bore you with plugging the values in, the H final you will get is about 1.28 meters. I think 1.3 with 2 significant digits. Okay. All right, we'll do one more problem. And so this last problem will be number 28. Number 28, we have a child. He or she is going to be sliding down the slide. So let's just say that this is the slide. And she has a mass of 16 kilograms. The initial height that she's at is 2.20 meters. And when she gets to the bottom here, she's going to have a final velocity of 1.15 meters per second. And this time we want to know how much thermal energy due to friction is generated in this process. So here's going to be the thrust of a lot of these problems. So as we said before, our energy states are going to be conserved. That means the energy that we started off initially is going to be equal to the energy that we have in a final state. Should be meters per second here. So let's see if we can kind of factor that in, along with, this time we're going to have friction involved in here. So there's friction. So we'll have something that looks like, again, E naught, E initial is equal to E final, and our E initial is going to be equal to, again, nothing new, 1/2 mv naught squared, and mgh initial, and our final state is going to look like 1/2 mv final squared plus mg h final. But this time we have to factor in the fact that friction was involved here. And how friction gets factored in is by way of determining its force times the displacement amount. So on the right side of this equation, we're going to need to also factor in the force of friction, in this case kinetic friction, multiplied by the length in which he or she went. So in this case, this distance right here would be d. Okay. And so we're not going to be able to find d per se, I don't think, and that's okay, because what we're trying to do is we're just trying to figure out this last energy piece that I put in here. So this is that energy, right? Remember, that was our basic definition for work. The work done by a constant force that's being pushed over a specific distance. So we're going to assume that friction is constant throughout the slide here. Okay. So we're not going to be trying to clean that up anymore. We're just going to work with what we have right in, get my pen to work, right in here. So we're going to just use that equation all over again. All right, almost done here. So let's write it over one more time. We'll have to rewrite these. Just move this up a little bit. Move this up. And get rid of that. So it looks like that equation. All right, so our goal here, again, let's go back. How much thermal energy due to friction was generated? So we're solving for that piece right there. Let me state that again. We're solving for this piece right in here. All right, so let's start to move things around a little bit and see what we get. I'm going to move this piece to the other side. I'm going to move this piece to the other side because I just want to isolate that Fk times d. So 1/2 mv naught squared, mgh naught, is 1/2 mv final squared minus mg h final is equal to that force of friction, in this case it's kinetic friction, times the displacement or the distance traveled. So let's keep in mind a couple things are going to go away here. Our initial velocity, when we start off, we assume that the child had no initial velocity. It started from rest, so we can send that to 0. And we're going to say that the ground is going to be our final height. So at this point right here, this is our H final equal to 0 meters. And so we have that nice formula, and let's see what we get. So now we're ready to just simply plug in. So how about, let's see, she was 16 kilograms. So 16 times 9.8 times her initial height, that was the 2.2 meters, minus the 1/2 times 16 times her final velocity, which is that 1.15 meters per second. And that's going to give us these units. That's going to give us some number in joules. So when you do the math on that, you should get 334 joules. Okay. So work through those problems.